The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
So I'd like to invite Dr. Ken Elwood from the University of Auckland up. Ken?
Hi, thank you very much for sticking around for the last presentation and the last session of the last day. Thanks very much. You might wonder why people from Chile and New Zealand are coming here talking to you about repair. Well, of course, it's because we have earthquakes. It is a real challenge immediately after the earthquake to determine what to repair, how to repair, what that building is going to be like in a future earthquakes. Because once you've had an earthquake, there's guarantee that you're going to have further because you're going to have aftershocks. And we're seeing more and more that sometimes those aftershocks are actually larger or just as damaging. These questions of repair and residual capacity are really prominent in the minds of those who are going through earthquakes and really central to recovery and resilience of our communities. I'm pleased that we're able to come here and share some of these experiences with you, and I'm pleased that there's interest here in the U.S. On these topics. I want to first note my co-authors and really primary author, Kai Marder, is my PhD student, is just finishing at the University of Auckland. So while the prior two presentations have been on walls, I'm going to talk about here about beams. And really, it's good you've already heard the motivation from Chris around the damage in Christchurch. And so the questions that came out of that were, what are the implications of that damage that's seen in those buildings? And these are just two pictures of, as structural engineers, we think of this as beautiful performance, right? Nice plastic hinge in the beams, the columns don't have any cracks at all, great performance. But of course then the question is what's the implication of that damage for the future? What's the capacity in that damaged state? And if you do repair, what's the capacity of the repaired beam? In this case, I'm going to focus on epoxy repair. I'll touch on a more significant repair at the very end. I'm going to focus here on moderate levels of damage as compared with the prior two presentations. In New Zealand, where there's a very high insurance penetration, if there's severe damage to a building, the decision on that building is really quite easy to make. And in most cases in New Zealand, if there was severe damage, the decision was a full payout and the building was typically demolished. And so those are really the less contentious cases. It's really more the moderate levels of damage like the cases I've shown here. What is the capacity of those hinges for future earthquakes? And we define moderate damage as no crushing of the core, no buckling of or fracturing of reinforcement, and no wide shear cracks. Okay, nice, dependable flexural response. I'm going to focus on beams here, but there will be a few things that relate to columns and walls. We did a test program at the University of Auckland to explore these issues. We did 14 identical beam specimens, beams oriented vertically just because it's easier to test it that way. These beams complied with both ACI 318 as well as the New Zealand standard NZS 3101 for a ductile beam. All of these are summarized in this reference I have shown at the bottom there. We also tested some of these beams with axial restraint. most without axial restraint, but some to show the difference in behavior when there's some degree of restraint to axial elongation. This won't be the focus so much of my presentation today, but there are distinct differences in the behavior when you have that restraint. One of the things that we really was interested in is the effect of the loading from the prior earthquake and the effect of different loading protocols from different earthquakes that we might get on residual capacity. And so we looked at several different loading protocols, your standard cyclic type protocol, of course. But then we did several where we put in the rotation demands that a beam would have experienced during an earthquake. That's what's shown in red. And then we cycled it to failure, with all cycles being at or above the peak drift from the prior earthquake input. And I note that those the red inputs were done dynamically, so the right strain rate from the earthquake. And we also did this one test in the bottom left there. It's called psych no earthquake. That's to say what is the response of the beam without the earthquake having happened. And that provided us a nice benchmark for a lot of cases. We looked at both long duration earthquakes that you might get from a subduction event with lots of cycles, as well as a short, sharp pulse type earthquake. See what the difference was. Took them to different drift levels, 1.4% and 2.2%. So I'll use a mixture of these 17 specimens as I go through this talk. So first of all, let's talk about the effect of those moderate level loading cycles. And when I say moderate level, this is up to about 2.2% or so. And so what we've plotted here is the monotonic response of one of the specimens. That's the solid black line. And then you see the cyclic protocol, all those cycles there that you might expect. And then the so-called psych no earthquake. So this is the one where we've removed all of those cycles prior to 2.2%. For that, I'm just showing the backbone. That's the dashed line there. And you see that it's almost a perfect match, right? And so we conclude from that there's basically no change in your deformation capacity for those lower level cycles, okay? Above that, certainly, but not, and that's still a fairly significant drift, right? 2.2% just on the beam hinge. So I think that's quite reassuring for us because there's a lot of uncertainty as to what those cycles might be in an earthquake. So for a ductile hinge, that's very reassuring. We also looked at it from the point of view of energy dissipation. And so what we show here is the energy dissipation with the peak drift as the test progresses. And so the plots you see sort of increase in different ways up to that 2.2% level, because those are all the different loading protocols up to that 2.2% level. But then they all follow the same protocol after that, and you see there's really no difference in the energy dissipation beyond that 2.2% level. And so again, there's no real impact of those prior cycles on energy dissipation. Again, that's a good outcome for us. So now let's look at the reinforcement. There was a lot of concern in New Zealand about the strain capacity of the reinforcement that may have gone through a prior earthquake. The issues, let me just sort of illustrate graphically here what issues they're concerned with. So I show just graphically a stress-strain response of a typical reinforcement pulled straight in tension monotonically. That's the dashed line shown there. And then the gray line shows, maybe a simplified cycle that you might get during an earthquake where you have some residual strain at the end of the earthquake. And then what is the strain capacity of that bar if you pull it again? And you tend to see an increase in the strength of that bar when you pull it, and you tend to see a reduction in the uniform strain, or the strain capacity of the bar. And that's really from two effects. From a low cycle fatigue effect, where you just can't take as many cycles, and a strain aging issue, where depending on the metallurgy of your steel, the steel can become embrittled after having seen the prior strain, and it rests for something on the order of a few months. So let me talk about each of these two issues, and for the most part, I think I have good news. So we looked at reinforcement and looked at this low cycle fatigue problem by putting them in a clamp system and cycling them. Note that we kept these clamps very close together to avoid buckling of the bar, because we didn't want that additional strain that comes with buckling. So it's a 4 dB spacing of the clamps. And what we did is we imposed a strain demands that we saw in our reinforcement in the beam tests. And that's one of the beam tests where we had a long duration earthquake. So I had many, many cycles, and we actually amplified this to give us a higher strain demand. So we really pushed the bar up to a strain of 6%. And then we pulled it to failure. And what we see is really no difference in our strain capacity, whether it's gone through those prior cycles or whether we just pull it monotonically, which is the red line. So that's good news. For a long duration earthquake, we haven't really seen a reduction in the strain capacity of this particular bar. Okay, so what about the strain aging issue? And here I'm showing test data from others where they have they've done prior straining of the bar to different levels, that's on the x-axis, and then let it sit, and then pulled it to failure. And what's shown on the y-axis is the total strain required to go to failure. And what you see is that pre-strain results in a drop in your strain capacity. And that's the strain aging effect, the reduction in that strain capacity. But for this type of reinforcement in New Zealand, this is grade 300, so that would be somewhere around 45 KSI steel. The strain capacity of the bar is quite significant already. And even with that reduction, you're still above the limits that are typically applied in New Zealand guidelines for seismic assessment of existing buildings. So while there is a reduction, it's not a reduction that is a significant concern, putting us below those limits. But what if we put those two together? What if we put strain aging and low cycle fatigue together? So this is a plot showing the number of cycles to failure for different strain levels of those cycles. And it's a log-log plot. I'm not very keen on log-log plots, but that's what I was given. But what we see is that for large strain cycles, you can actually see a reduction in your remaining cycles to failure by up to 50% if you have that strain aging beforehand. That's pretty significant, a drop in your number of cycles to failure of 50%. But those are at relatively high cycle numbers. You look at this x-axis, most of those are numbers of cycles that are well beyond those cycles that we're concerned about in earthquakes. And the strain levels are pretty high. Typical pulse-type ground motion will have very few of those significant cycles. A typical subduction ground motion might start putting you into the range where you might be concerned. Okay? So I think there's further research needed to really understand the expected number of cycles that we see in different components in different earthquakes. But I also note that this test was done with S/dB of 6. And here I show some photos from some of Wasim's work where he shows that you do get some curvature of the bar at S/dB of 6, and that really puts your strain even higher. And so if we were to look at our moderately damaged component, which has not seen buckling, maybe you do have tighter spacing of your transverse reinforcement, then I think we start to get away from this issue as well. Okay, so that is potentially a concern. But what does moderate damage, how much does it really reduce our residual capacity? Now let me just illustrate that with these 4 cases, 3 of which have gone through earthquakes to just over 2% damage, and the last one is our benchmark case of no damage and only cycles above 2%. And what we see is that from a strength point of view, there's really no change. And what I'm showing you is the first cycle after having gone through the earthquakes. From a strength point of view of a ductile member, of course, there's really no change. Stiffness, absolutely. That's been highlighted by everyone so far. Significant change in stiffness. Deformation capacity is not quite captured there, but let me actually show you a next slide. Well, here I'm showing you the drift at a 20% drop in strength, so a typical definition of drift capacity, versus the number of sliding planes that develop in that beam. And that's really the way in which most of these beams fail, is sliding shear after growth on a single plane, on a plane. And what you see is that in those cases where we're able to develop more cracks, more sliding planes, then you're able to get a higher drift capacity. And that makes sense, but note that all of those drift capacities are greater than at least what we would assess based on the New Zealand standard as your drift capacity of such a member. So they're still all at reasonably high levels. But what this means is that maybe the number of cracks is a good indicator for how much damage you have, or what performance you might get in a future earthquake. Number of cracks. So remember that. We'll come back to that. How about then the key thing that you lose is really the stiffness. And we know this, of course, from past research, typical Takeda model, that on a returning cycle, you've lost significant stiffness in your element. We wanted to quantify that for elements that have gone through an earthquake loading, as opposed to elements that have gone through cyclic loading. And so we collected shake table test data in addition to our beams that had gone through the earthquake loading prior. And we looked at the drop, the vertical axis, if you can't, it's small rating. So it's the drop in stiffness compared after the earthquake compared to before. What we see is that this is nicely bounded by a function of 1 over the ductility, which is quite a convenient, simple parameter. It gives us a conservative estimate of the drop in stiffness. You might want to drop it down further at the low ductility demands, between 1 and 2, because of that's where you get such a steep drop in stiffness and the uncertainty of really getting that ductility right. But what this tells us is that we really need to know something about the peak drift demand or the peak ductility demand from the prior earthquake. So how do we estimate that peak deformation demand from the damaging earthquake? It's clearly important for our stiffness, and really there's no sense in going through a detailed assessment of a building, of a damaged building, if you can't understand how it performed in the first earthquake, right? So understanding that peak demand from the prior earthquake is really critical. Most standards or most procedures out there for post-earthquake assessment, including FEMA 306 that was brought up earlier, use cracks, crack widths, maximum crack widths as your primary metric. If you look at this plot here, it's looking at the peak drift from the prior earthquake to the maximum residual crack width. And we see we really can't make a correlation there. And that's largely the randomness of different earthquakes are going to give you different crack widths for different peak drifts. If we look at two particular cases, two particular beam tests, one with a long duration motion, the other one with a pulse motion, but the long duration only taking it to a peak drift of 1.4%, while the pulse motion taking it to a peak drift of 2.2%, but we get the same maximum cracks, and we get the same elongation in the beam. And that just has to do with the way in which the pulse motion affects the beam versus the way the long duration motion affects the beam and the growth with the number of cycles in the long duration case. So residual crack widths are not very reliable in relating to the peak drift demand that the building experienced. So what can we do? Well, like I said, it's perhaps not so much the maximum crack widths, but more sort of the distribution of cracking that is important. So this is a plot of the number of cracks wider than 0.2 millimeters within the plastic hinge region. And there, while there's still quite a bit of scatter there, there is more of a consistent trend. And maybe we can pick a bound on that and use that as guidance to what our likely peak drift was in the prior earthquake. And what this shows to us is that at, if we only have one crack at 0.2, wider than 0.2 millimeters, that's not necessarily a concern. Really what it's indicating is that we didn't necessarily have that much demand. There was a concern amongst engineers in New Zealand that a single crack presence in a beam meant that you had very large strains on your bars, and maybe you had strained your bars too far because you hadn't distributed your cracks. But in fact, what it may have been showing us is that those particular beams didn't see large rotation demands. To determine that specifically, you need to look at your quantity of reinforcement, see if you're over minimum levels. But I caution, all of what I've been talking about here is for beams that can grow, beams that don't have axial load on them. For columns and walls, you tend to get this response. This is plotting elongation versus drift. You tend to get this response where you always come back down to zero at zero drift, or your elongation is squashed. If your elongation is squashed at zero drift, then your cracks are also closed. And so using cracks widths is even more troubling for columns and walls. And I think there's some future research needed here to relate the damage to columns and walls with the peak drift demand from the prior earthquake. So now I'll get to the repair. We did a simple epoxy repair of most of these beams, of three of the beams, and with professional help, I should say. And we were able to restore most of the stiffness. So the unrepaired beam had a stiffness that was about 30% of the original beam, and the repaired beam got that back up to about 90% in this particular case. Seeking out more data in the literature of repaired beams, and there aren't many out there that have very reliable data to work with, but from what we could find, we felt we could reliably get about 80% of the stiffness back. Okay? So that was fairly consistent for beam specimens. But I note this one value down here. This is totally burnt out, but that one column specimen that's called out down at 50% or so. This is that issue perhaps of the fact that the cracks have closed. You're not able to epoxy inject those cracks. You're maybe not even able to identify those cracks. and the column is softer in the subsequent earthquake. And that may be a concern for drift-sensitive components within your building. If you've got a softer building, likely to see larger drifts and aftershocks. So I think, again, further research necessary for columns and walls in that case. One issue, though, is that you lock in your strain demands on your bars when you epoxy inject. So if the beam has already seen this elongation, and along with this elongation is strain in the bars, then you epoxy inject, you've locked in that strain. And so what I've shown here is the elongation that occurs in the beam. The first one is for one that was just tested by the earthquake, for the long duration earthquake, and then not repaired and tested to failure. And you see the black line on the left-hand plot. It just starts sliding back and forth because then it's a sliding shear failure and it's not growing any further. But then when we repair that the beam has been subjected to the same loading protocol. So the middle plot, you see that you have further elongation with the subsequent cycles, the black line continuing. I wish I could point with this. Yeah, the black line that continues up above those red cycles. And so now you're getting more elongation, more strain in your bars. And then the next one is just showing that is essentially consistent with the elongation and strain in bars that you would get for an undamaged specimen. So you're getting twice the elongation when you lock that in. But you essentially, in that post repair, you get an increase in strength. And that's really due to the fact that you've strained your bars and from the prior earthquake, and so you've got a little bit of strain hardening in the repaired beam. And then the deformation capacity is roughly the same for that repaired epoxy beam. So I'd like to end with just a case of a more significant repair. This is consistent with the wall repairs that Chris showed. We took one of those tests where from the prior 17 set, and it had buckled only on one side. The bars had buckled on one side, and so we replaced the bars on one side in the manner similar to what Chris showed, and left the other side as it was. So those bars had been strained, and they'd sat there for now about 6 months. So they had experienced strain aging. Then we poured concrete in that new hinge region, and we tested it. I tested it again to failure. One more time. There we go. And what we saw was that, and the plot down here in the hysteresis, the negative drift is putting those prior strained bars, those strain-aged bars, into tension, whereas positive drift is putting the repaired bars into tension. What we ended up seeing was that the repair bar fractured due to a concentration of strain right at the end of the weld. And the strain-aged bars showed us the effect of strain aging in terms of the strength increase. You can see the gray hysteresis there going quite a bit higher than the original cyclic envelope, showing us that strain aging has increased the strength of those bars beyond just what the strain hardening of the prior loading would have done. But in the end, we did not fail those bars. So the strain capacity of those bars did not come into play in terms of limiting the capacity of this beam. It was really the repair technique that was used on the bars on the other side that limited the capacity. So with that, I've covered a lot of material here, but just sort of 3 points to take away. The prior loading cycles below 2% really have minimal impact on the drift and energy dissipation capacity of the elements. Residual crack widths don't always provide a reliable estimate of your peak drift demands. Be careful about using those alone. And prior earthquake loading results in a reduction in stiffness that is proportional to the ductility demand, and we can recover a lot of that for beams, but with epoxy injection, but still further work required for that on walls and columns. Thank you.